Okay, in this video we'll talk about conservation of momentum. Um, so we know that if we have an isolated system, it is one in which the net force acting on it is equal to 0. So an isolated system means the sum of the forces are equal to 0, right? So the system itself is at equilibrium, right? It's not being accelerated. But we also know previously that impulse, which is a change in momentum, is a force applied over a time interval. So if we have a net force, actually this should have been stated as a change in momentum is equal to a net force acting over some time, or the sum of the forces acting over some time interval. So if we have the net force equal to 0, then this means that the change in momentum is equal to 0. If the net force is 0, then the change in momentum is equal to 0, because time, either that or the force acted over 0 time, which there's not a lot of sense in talking about the force acting at all if it didn't act over any time whatsoever. So if the sum of the forces, if the sum of the forces are equal to 0, then the change in momentum is equal to 0, and the change in momentum is the final momentum minus the initial momentum. So if we have an isolated system, so if our system is isolated, then there's no net force, and therefore the change in momentum, which is the final momentum minus the initial momentum, is equal to 0. So then we can say that in an isolated system, we have the initial momentum equal to the final momentum. This is what we call conservation of momentum. In an isolated system, we have a no change in momentum, or the initial momentum is equal to the final momentum. This is particularly useful in collisions. So this is conservation of momentum. Okay, so a couple ways. So we have to have no net force acting on the object. So let's say that we have a couple cases here. We have a frictionless surface, and then we have two blocks which are sliding along it. So I have block A with mass A, and I have block B with mass B. Now, if I consider this system to be these blocks, and it's frictionless, so that way the coefficient of kinetic friction is equal to 0, and these both had some initial velocity, VA, and this is VB, then this is this system here, these two blocks, has some total momentum, right? And what I'll do is I'll say this is the initial condition, or before the collision. They're going to collide. Clearly they're going to collide. It's on a frictionless surface, so they're not going to stop. So we're going to call this before, or if you want to, you can call this initial. So our momentum before, the initial momentum, is equal to the mass of A times the velocity of A plus the mass of B times the velocity of B. And then this is, I'm going to put all of this in parentheses and put an I here for initial. So the initial momentum is just simply the momentum of the system before the collision. So there's no friction there, so it's isolated because there are other forces. There is a weight acting down, but there's also a normal force acting back up, such that the net force in the y direction is equal to 0, right? So we have it, it's isolated. Now, after the collision, we would have here, so this is a dividing line, not another surface. I draw the same surface here, and this will be my after picture, or my final condition. And I'll draw the boxes again, but after they collide, I suspect that they will probably bounce off of each other a little bit. So I have mass A here, and then I have mass B like this, and this will probably have some velocity back like this. I'll call this VB. This is final, and this is VA final. Let me give some extra subscripts here. VA initial, VB initial. So my final momentum is going to be, well, again, I have my total momentum final. I'll just say final momentum is going to be mass of A times velocity of A plus mass of B, velocity of B in the final condition. Since this was an isolated system, I know that the momentum before is equal to the momentum after. This follows from the fact that what we said before, if the change in momentum is equal to 0 because there's no forces on it, then this means that the initial momentum is equal to the final momentum. So we have here mass A, velocity A plus mass B, velocity B initial is equal to mass A, velocity A plus mass B, velocity B, all in the final condition. And this is what I have for two objects colliding together on a frictionless surface. This is the conservation of momentum with these two objects. The initial momentum is equal to the final momentum. This is not to say the velocities are the same. Clearly the velocities change, right? This one turned around. Actually, both of them turned around, right? But their total momentum, when you add them up as vectors, remains the same. Another way we could have had this, we actually could have had a surface with friction on it, but in this case, maybe we have, here's block A, and we consider the point just before impact. So there's a tiny little bit between here. This is mass A, this is mass B. Let's say that our coefficient of kinetic friction is not equal to 0 here, so we have a rough surface indicated by these hash marks. We have a rough surface here. But another way that we could look at this is you can say, well, this distance is not very large, so the time interval would approach 0. Remember that a change in momentum is equal to a force applied over a time interval. If this time interval is small enough, then we could approximate this as about equal to 0. So we could actually technically have even rough surfaces have momentum conserved, but only if we consider the momentum just before the collision and then just after the collision. So we would still have the same case. This would result in the same equation up here, but we need to consider them right before they hit. We have to be very careful. I can't take, if I have friction here, I can't take my velocities way back over here. I can't take this velocity there and that velocity there and give friction all this distance and time to work. I have to be very careful to have my velocities just before the actual collision, which will be important when we're combining conservation laws together later on. So we might just consider them right before the collision as opposed to some vast distance apart. Interesting things about conservation of momentum here. If we go back to projectile motion, think back to this. We have Remember, if we have some object here being launched up at some angle, then it continues along this path here, right? Now, we memorized over a while that the acceleration in the y direction is equal to downwards gravity, and the acceleration in the x direction is equal to 0. These were the assumptions that we made for projectile motion. The acceleration in the x direction equals 0 meant that the sum of the forces in the x direction equals 0. This came from ignoring wind resistance. So we said that the acceleration was equal to 0 because there was nothing to slow it down in the x direction. However, we couldn't say that with a y direction because there was gravity to pull it downwards. So, interesting thing about projectile motion here, we have, if we look at this, this has some initial momentum in the x direction, px initial, and it also has some momentum in the y direction, py initial. In the final condition over here, when it lands, or right before it lands, then we also have momentum in the x direction, px final, and we have momentum in the y direction. This is simply the mass times velocity in the in that particular direction. Oops, I apologize. What did I just do there? Sorry about that. This is obviously the y direction, and this is the x direction. Because there were no forces acting in the x direction, we have momentum is conserved in the x direction. So I can say that momentum in the x direction initial is equal to momentum in the x direction final. So they have the same momentum. And the ball clearly has the same mass when it was launched and when it lands, unless it's radioactive and it's decaying throughout its path. Then the velocity, we know that v naught x, this came from acceleration x is 0. We said that v naught x was equal to v final x. And so since the mass is the same, the velocity is the same, clearly the momentums are the same. However, this is not true in the y direction because gravity acts on it. Clearly, our momentum changed here. It was upwards initially, upwards momentum, and then it was downwards final. And this follows everything that we know about the velocity changing direction in the y as well because of the acceleration due to gravity. So the key thing to take away with conservation of momentum, and momentum is conserved in any collision. There's not, if I consider back to this drawing here, or actually I'll think about two balls colliding. I have mass A and I have mass B. If my system is these two masses, then any interaction between these masses is an internal force. So there's no external forces. The sum of external forces acting on this, sum of external forces is equal to 0, as long as I have frictionless environment, that I don't have to deal with the interaction between these two. So as long as I consider both of my particles to be my system, or if I have 3, 4, a million particles, if I consider all those particles which are going to interact with each other to be part of my system, then momentum is conserved in any collision with those particles. So the key to conservation of momentum problems is to draw before and after pictures. So we always draw a before picture. Maybe I have, this is A, this is B, velocity of A, velocity of B. This is all initial. You can say before or initial. And then we have an after picture after the collision or in the final condition. Then we have A and we have B, and we would need to be told something about how they are moving and something about their masses in order to discover more information about it. but we would have our initial momentum here. We would calculate this, mass A, velocity A, plus mass B, velocity B, and then we have a final momentum here. We calculate these momentums, we calculate them separately, and then set them equal to each other if we have an isolated system. So the initial momentum is equal to the final momentum. So this is the key. So we draw before pictures and after pictures. Or even if you wanted to, you can always label this 1 and this 2. Before initial 1, after final 2. I will leave the subscripts up to you.